Or the next, this is, yeah. The next talk is by Jorge Garcia Rojas, and he tells us about 2D spectroscopy of galactic planetary nebula with high abundance discrepancies.
Okay, hello, good morning, everyone. First, I want to thank the organizers for giving me the mic. Use the mic. Okay. I want to thank the organizers for giving me the opportunity to present this work. This work has been done in collaboration with all these people. Well, let's start with a little bit of context on the abundance discrepancy problem. In a seminal paper in 1967, Manuel Painberg did a theoretical work in which he predicted that in the presence of temperature fluctuations parameterized by the T-square parameter, the temperature in the gas computed from the collisionary accepted lines was going to be overestimated with respect to the real average temperature of the nebula. This is owing to the extremely high dependence of the emissivity of collisionary accepted lines on the electron temperature. Later on, in the 80s, this problem was related to the problem of the abundance discrepancy, which is consists in the fact that the abundances computed from the faint optical recombination lines are always higher than the abundances computed from the bright collisionary accepted lines for a given ion. So this is parameterized by the ADF, which is the ratio between both abundances. So what is the problem? The problem is that photoionization models cannot predict the high enough temperature fluctuations to recover the ADF. So maybe Fueli Viegas suggests that maybe photoionization is not enough. On the other hand, there are several planetary nebula in which very high ADF have been computed. This requires implausible T-squares. So maybe, well, in several years ago, we proposed that maybe H2 regions and planetary nebula ADF do not seem to share the same origin. And this is, in the last years, we have worked a lot on that. And my former PhD student, Eduardo, wrote a very nice paper in 2023. And it was published in Nature. And he found that when you compute the temperature fluctuation parameter from the observed ADF, and you relate to the difference of the temperatures between the high ionized zone and the low ionized zone, you found a clear correlation if you use data from H2 regions and star-forming galaxies. This can be explained if you have in your ionized region temperature fluctuations only in the inner part of the nebula. And the real average temperature is the temperature of the outer part where you not have temperature fluctuations. But what is the problem? The problem is that this does not work in planetary nebula. There is not such correlation. Maybe this is owing to the fact that in planetary nebula we have several objects. We have here the ADF of oxygen, and we have the green points, the green objects are planetary nebula, the purple ones are H2 regions, and in planetary nebula we have several objects with very large abundance discrepancies, over a factor, almost a factor of 1,000 in some cases. And the blue ones are interesting planetary nebula with no close binary central stars. So these large ADF require a plausible temperature or density fluctuations and can be only explained by chemical homogeneities. Photoionization models have predicted that if you combine a hydrogen poor cold gas with a normal temperature warm gas with hydrogen rich, you can reproduce the ADF observed. And in fact, we observed with the blue tunnel filter of Osiris, the planetary nebula NGC 6778 in 2016, and we found that the emission coming from recognition lines of oxygen show a very different spatial distribution than the emission coming from collisional excited lines. So this is an indication of maybe the presence of two different plasmas. This one is emitting in a hydrogen poor cold plasma, and this one is a hydrogen-rich warm plasma. This motivates us to obtain Muse data to do a deeper analysis. Well, we have seen very nice Muse data in this conference from Anna, Konstantinos, Lydia. And we found that, well, a surprise, if you compute the map of the electron temperature of nitrogen-2, you found that the central parts of the nebula were very hot. This is owing to the strong recombination contribution to the auroral lines you are using to compute the temperature. So you need to correct that recombination contribution to have the temperature of the warm gas. This recombination contribution in the spectra is coming from the cold gas. So you need to correct, and you need to assume a temperature of the cold gas. If you don't have a diagnostic to compute the temperature of the cold gas, you are dead. So in this case, we didn't have a diagnostic of temperature, so we play a little bit with assuming different temperatures, and we correct when we found that more or less the temperatures were homogeneous. We also compute the ADF maps and found a well-known result that Harriet and other people have found in different long slit studies, that the ADF peaks at the central parts of this planetary nebula. But there is a problem. If you have two components emitting the recombination lines, the metal recombination lines, and another very cold gas, hydrogen poor, and you have another component emitting the warm gas from the warm gas, emitting the collisional excited lines, but the abundances are computed relative to hydrogen, and hydrogen is in both components, in the hydrogen poor and in the hydrogen rich. So you have a degeneracy there. Well, the only way to break the degeneracy is playing with photoionization models. We did in collaboration with Christophe and Veronica Gomestiano, a former postdoc in my group, some toy photoionization models, and we used the computed collisional excited line temperature, the hydrogen temperature computed from the Paschen or the Balmer jump, and we use, assuming different temperatures for the cold phase, you can compute the weight of the hydrogen poor and hydrogen rich gas. And then using some simple equations, you could compute a map of the weight of these two components. This was possible because for this planetary nebula, which is NGC 6153, we had very deep data computed by Michael Richter, US data, and where they compute a precise temperature of the oxygen recombination lines emission region. So we can compare the map of the ADF with the real abundance constant factor. So even the problem is even higher. So you are going to have much higher abundances computed from the recombination lines, and well, they're slightly affected by this the abundances from collisional excited lines. There is another way to approach to this problem, which is using kinematics. In this case, Michael Richter did a lot of work on this in the last years. So he has taken advantage of UBES and used it as a small, very small IFU, and did a lot of position velocity maps and found the same results. There are differences in the kinematics of the gas emitting oxygen to oxygen recombination lines and oxygen-3 collision acceptor lines, and the emission seems to come from the central parts of the nebula. For a more detailed view of this problem, please stay tuned to the next talk by Hao Miao Huang, who has done this kind of analysis in other planetary nebula. Well, and what regarding the warm gas? Well, we know that we have some temperature fluctuation, some chemical inhomogeneities, but maybe we also have temperature fluctuations in the warm gas. And to check this, we took advantage of the SIRE database, which is a database of very deep planetary nebula data compiled by a group at the IAC. And we, well, this work has been led by my student, Elena. We compute for a relatively large number of objects the temperature of argon-4, which is a temperature of the central parts, more central parts of the planetary nebula. And we found that the observed relation between the argon-4 and oxygen-3, which is predicted by photonization models to follow more or less the 1-1 line, is not followed. So, in principle, the temperature, argon-4 temperature is hotter than predicted. So maybe there is something going on in the central parts of planetary nebula also, and maybe this is a signal of the presence also of temperature fluctuations. Well, regarding the last advance, I want to show you some very preliminary. This is paper that is about to be submitted with a WIF project, which is an instrument that has a large IFU, more than 1 arminic square. This is led by Janet Wu and Roger Wesson. And in this first study of the Green Nebula, we have found this emission here is a coronal emission of iron 5. We also find coronal emission of iron 6, following the same morphology. And this is very interesting because Ana Monreal show similar founds in other planetary nebula using MUSE. And the nice thing here is that we have found that this iron emission comes compared with emission of recombination lines. This is a carbon-2 recombination line and oxygen-2 recombination line. It seems that is in between the peaks of the emission of the recombination line. So maybe something is happening there. The fact that iron is emitted here so strongly is a clear fact, a clear proof of dust destruction. And is ionized because the iron released from the dust and then is strongly ionized by the strong radiation field of the central star. Well, another instrument that is coming to study the central parts of the planetary nebula is MAD. Dave Jones is the project scientist of this instrument, and it's going to be nice because it's going to cover the whole range. So we can go there and compute temperature-sensitive oxygen recombination lines diagnostics. And this is an example of simulated images made by David Jones and Veronica Gomez-Llanos of the M142 planetary nebula. So it's going to be nice. We are very excited. It's coming to the telescope on November, December. So it's going to be very exciting. And for the future, of course, Blue MUSE, we need to extend to the blue. Blue MUSE is going to be fundamental to these studies. And for, well, in relatively mid-term, long-term, the wide field spectroscopic telescope, which is going to allow us to study more extended planetary nebula, going to the large field of view, is the case of the abundance discrepancy factor is in the white paper of this instrument. Well, I'll leave you here my conclusions. The important point is that extending wavelength coverage to the blue in the IFO studios is very important, and the upcoming data from WIB and MAT will be crucial to shed some new light on this problem. Thank you very much.
Thank you. Questions?
Actually, more of a comment in talking about the higher electron temperatures found for the higher ions. Going back to ISO observations by Vikram and Potash, they found that trend in many planetary nebulae. And it was a little puzzling. I'm not sure if you know, familiar with those papers.
Which year? Which
It's 2000, late 90s with ISO. And so they had some rather high ions. And they were mostly getting, they included some UV data as well, archival UV data.
I'm going to
But
check.
they found a trend in most planetaries with temperature, electron temperature higher for the higher ions.
Okay.
Another question?
Hi, thank you for the talk. Regarding like this temperature in the magentics, well, I'm thinking about in the innermost part of the planetary area, well, we would expect that there's a hot bubble there, right? So wouldn't be the mixing between the hot and the photoionized gas causing this kind of temperature in the magentics, because at the end of the day, your mixed material that could be
Yeah, probably. The important point here is that if you use only photoionization models, you do not predict that high temperatures.
Yeah.
So of course there should be something more there, and this is maybe the region of the presence of temperature fluctuations there. So some feedback, some bubbles, etc., some shocks, you know.
okay. Thank you.
Okay, then let's move on to the last. Now, let's thank you again first. Last talk of the session by, I hope I pronounce it right. Meow. Wow.
Okay. First, thanks, Gazaro has introduced my work in his talk. I am Haomiao Huang. I'm a PhD student from NAOC, and my supervisor is Xuan Fang, and these are all of my collaborators. The topic of my talk today is for kinematic study of high ADF. We know PNE are the descendants of low and intermediate mass stars. At the end of their life, these stars expel their outer layers through strong solar wind, forming glowing nebulae and contributing to the chemical enrichment in the interstellar medium. Because the low and intermediate mass star constitutes the majority of the stellar populations, PNE are current important contributor to the metal cycle in the local universe. The abundance description is a classical problem in the study of gaseous nebulae. Analyses consistently show that the recombination lines yield higher abundances than their CEL counterparts. This phenomenon is widespread in gaseous nebulae, most typically small in H2 region and most ADF. However, a few PNE exhibit extreme ADF values, and the origin of this extreme ADF is still unclear to date. Early deep long-slit spectroscopy indicate that the OIL emitting region comes from the region closer to the nebula center, and the subsequent I-view observation has further confirmed this. It is generally thought that metal-rich low-temperature clumps are likely exist in high ADF PNE. Additionally, statistical study has revealed that the binarity of the central stars is correlated with the ADF. PNE hovering short period binaries are likely to have higher ADF values. To understand the origin of the extreme abundance discrepancy, we carry out a morphokinematic analysis of high ADF PNE. We carry out a comprehensive analysis of VLT UV's deep spectrum of high ADF PNE. And here, the UV spectrum has very high resolution and wide wavelength coverage. The observations utilize a common slit width of 2 arcsecond, but the slit length differ between the red and blue spectrum. Here we present a 2D calibrated spectra of HF22. The high resolution and the substantial spatial coverage enables a detailed morphokinematic analysis. Due to the non-issue in the previous analysis in McNabb 2016, we performed a reanalysis of the 1D nebula spectrum. Due to the slit length and the central star position in the slit differ between the blue and spectra, our first step was to select a common extraction aperture across all wavelengths. Also, the selection was made with another considerations to minimize the contamination from the central stars or the field stars nearby. Here we present a 1D spectrum of HF22, and as you can see in the figure, numerous emission lines, including high quality optical recombination lines, is clearly seen in the spectrum. And we performed fundamental plasma diagnostics based on CELs, ORLs, and Balmer pattern jumps. And here we just present a few results. Overall, the temperatures derived from ORLs are lower than those derived from CELs, but while the Balmer and pattern jump temperatures fell in between. For densities, ORLs yield higher temperatures at higher densities. Ionic and elemental abundances as well as ADF are also calculated. Here we present the ionic abundances derived from oxygen 2 and neon 2 ORLs. And you can see that for different multiplets, abundances derived from different unblended lines are generally consistent. For ADF, our results are slightly higher than the mu spectrum, possibly due to our extraction apertures are located closer to the nebula center, while the ADF is higher. Now let's move on to the morphokinematic analysis. We first measuring the velocity splitting of various emission lines to estimate the expansion velocity, and constructing the Wilson diagram to investigate how the velocity of different types of line varying with the ionization potentials. We do not discuss NGC 6153 here, as Dr. Michael Rachel et al. In 2022 utilized the same data set, and our results are similar to that of theirs. For the other two sources, we found that the expansion velocities of CELs decreasing with the increasing ionization potentials, which is similar to that of the Hubble type flow kinematics. But for heavy element ORLs, including these lines, they show clear different trends. This finding stress that the kinematics of ORL emitting regions is different from that of the CEL emitting regions. We also analyze the 2D spectra. Here we present the result for M142 here. We began by constructing the position velocity diagram of various emission lines, and the central star position was set at 0. Our key finding is that the emission from different types of line originate from a different place, and they have different spatial and kinematical structures. The emission from neutral and low ionization species, such as these two lines, has originate from the outer nebula with hyperbolic shape structures, while for higher ionization species, their emission comes from the region closer to the nebula center. and this is also similar to the Hubble type flow. Here we present the PV diagram of several ORLs, and it can be seen that the structure of ORLs from light and heavy element ions are different. Additionally, ions with different ionization potential show different spatial and kinematical structures, and which is similar to that of the CELs. However, when focusing on heavy element ORLs, the PV diagram from lines from carbon 2 to neon 2 has the similar and their PV diagram are remarkably similar, despite differences in ionization potential of more than 15 electron volts. This suggests that the ionization structures in heavy element ORLs emitting regions differ from that of the CEL emitting regions. We also explore the temperature and the density structure of the PNE. Here we present the nitrogen 2 or CEL density temperature maps. And before recombination correction, it can be seen that the temperature in the nebulous center are unrealistically high. But after recombination correction, the ring-like structure seen in this figure was almost disappear in this figure. And the final corrected temperatures are lower in the center, although some residual still exist, and this residual is similar to that of the ORL PV maps. We also explore the density structures. In the right figure, we present the sulfur 2 density map. It can be seen that the central part has a higher electron densities. This may be due to a low signal to noise ratio in the nebulous center of sulfur 2 line, or the recombination contaminations, as we detected the sulfur 2 ORLs in our spectra, and this structure similar to that of the PV map of ORLs. Additionally, when looking at the argon-4 density, which comes from the higher ionization regions in the nebulous center, which means the argon-4 density is very low, which means that the true density in the nebulous center may be lower, opposite to the increasing trend seen in sulfur 2 map. This also demonstrates that these structures may be originated from optical recombination contamination. We also estimate the kinematic temperatures. We know that at the same temperatures, the larger the mass of the particles, the smaller the thermal bonding effect. Therefore, we select two lines from different species, H-alpha and helium-1 line, to estimate the kinematic temperatures. These two lines have similar structures, and their emissivity varies consistently with the temperatures. And these two lines has sufficient thermal bonding effect. We at different temperatures, at different assumed temperatures, we corrected the thermal bonding of helium-1 line and compared it to the H-alpha. And we found that at 6,000 Kelvin, the H-alpha to helium-1 to H-alpha ratio are the most uniform, and these temperatures were selected as the kinematic temperatures. We found that the kinematic temperatures is higher than the CEL temperatures, it's higher than ORL temperatures, but lower than the CEL temperatures. We also constructed the ADF maps. And before ADF map construction, we calculated the CEL and ORL abundances and then ADF maps. We found that the CEL abundance is relatively uniform, but for ORL and ADFs, they have clear trend. Along the spatial directions, the closer to the nebulous center, the higher the ADF. But for the velocity directions, in these regions, the largest deviates from the systemic velocity, the higher the ADF. Finally, we estimate the relative mass of H+ and heavy element ions in the cold and warm components. We calculated these parameters, including cold mass fraction of H+ in cold plasma, fraction of H beta from the cold component, and cold warm mass ratio of heavy element ions, as well as abundance contrast factors. our calculation indicate that the H+ fraction is low in cold plasmas, which means that ORL region is H deficient. However, that's such small amount of H+, such amount of H+ contributes a significant fraction of H beta emission from the cold plasmas, which explains the low Balmer and Parson jump temperature seen in this PNE. For heavy element ions, we found that their mass in cold plasmas are on the same orders as in the warm plasmas. This explains the large ACF we calculated, which means that the cold regions has higher abundances, which may be due to the metal enrichment or H depletion. That is all for my presentation, and this is a summary. We reduce the VLT UV deep spectra of high ADF PNE with absolute flat calibration. And the spectral analysis show that CEL and ORL has discrepancies. ORL yields lower temperatures, higher densities, and higher abundances than ADF. For kinematic analysis, based on Wilson and PV diagram, shows that CEL and ORL has distinct velocity structures, and ADF decrease outward. And our mass ratio calculations show that the plasma is hydrogen deficient but metal rich. And before ending my talk, I would note that another paper was published on the archive 2 days ago, and their results are generally consistent with ours. And I hope both papers can provide a clearer picture of the high ADF planetary nebulae kinematics. That's all for my talk. Thank you.
Thank you very much. Nice talk. And back the videos for the YouTube.
Are these planetary nebulae where you found the cold H deficient plasma related to Wolf-Rayet type central stars?
The HF22 it has the emission from the central star, like carbon-3 and carbon-4, and the other and the M142 is you can see that the central star of M142 is very faint, and we did not find any emission lines from the central stars. And the NGC 6153 we also did not find any. And the central star of HF22 we can see the hydrogen emission hydrogen absorption lines in this central star.
Okay, congratulations. It's a really impressive piece of work. But I think the thing that I think is most interesting, so tying together with what Jorge said about the ADF, being spatially distinct, so the cool gas is internal generally to the normal warm gas. It's really interesting that they are kinematically distinct, but not dramatically kinematically distinct. There's a small difference. So one of the hypotheses for the formation of the cool gas was that maybe it's related to some kind of eruptive event, something, because they have nova-like abundances, right? But the kinematics, they don't support that hypothesis at all, because the cool gas is not that fast, right?
The kinematic between the warm and cold plasma indeed is not significant, and we cannot demonstrate which hypothesis is the right, and this maybe need to further study.
No.
Yes, you use the general comment. You use the term Hubble-like flow. Hubble flow is the expansion of the universe. It's isotropic, homogeneous. There is no center. Okay, planetary nebulae, there is a center. It's not isotropic. It's not homogeneous. So don't use Hubble-like flow kinematics unless you do cosmology.
Homologous, you have to say.
Homologous, yes.
Yeah, thank you.
Okay, so it's now we know it's infinite. So Hubble-like flow, don't use it. It's not relevant. And many people use it, but it's not relevant. It's just linear, PV line. So this is it.
Thank you.
Last question.
Excellent talk.
Thank you.
Question for you and also for David. Is there any evidence of binarity in these stars?
Binarity.
Yeah.
The central stars of HF22 is a binary.
Okay.
And this was published in the Helwig 2016. And yes, and the binarity was and the light curve has shown variabilities in their light curve. Okay, that's all.
Okay, thank you.
Let's thank the speaker again. Then we have 4 more posters coming. The first one being by Sean from something. Sorry, I don't know how to pronounce things. You can pronounce yourself. Yeah, I know.
So, I'm Jean-François Desmos from National Astronomical Observatory in Madrid. And well, if you want to study the very inner layer of AGB stars with a very high resolution, one good option is to go for the VLBI, very long baseline interferometry, that can give you milliarcsecond to microarcsecond resolution. The bad side is that you need a very bright source with typically brightness temperature of 10 to 100 of million kelvins. So you need a nonlinear process, such like maser emission. But we're lucky, and AGB, it's common to find maser emission from several molecules like OH, H2O, SiO masers. And we are especially interested in SiO masers as they originate very close to the surface of the stars, just a few radii, the stellar radius. And we can reach resolution of microarcsecond. So with that idea in mind, we set a discrete survey with the 40-meter radio telescope of JBES. And we observed all the known symbiotic stars visible from the northern hemisphere above minus 20 degrees. So we have 84 sources. And we observed an instantaneous bandwidth of 18 gigahertz, centered on the SiO meter at 43 gigahertz, and with a spectral resolution of 0.2 kilometers per second. And we were quite lucky. We find more than 10 sources. 10 are very promising sources, like this one that is Scuti X1. And we have 4 tentative detection that we still need to confirm. Thank you very much.
So hi all, I'm Maria Gostachili from the Institute of Space Sciences in Barcelona, and the poster is about diagnostics for nebula identification using machine learning. Actually, my field of expertise is mainly supernova remnants, And so for the optical identification of supernova remnants, the most common, the most traditional, let's say, diagnostic is the Serpent over H alpha. So sources with this ratio higher than 0.4 are considered as supernova remnants. And this is an empirical diagnostic that they found people that studied the Small Magellanic Cloud, and it seems to efficiently differentiate shock excited from photonization sources. However, this diagnostic is biased against low excitation supernova remnants, and this is what drove me during my PhD to develop a new model-based diagnostics. So for this reason, I used shock and photonization models from MAPIX3. I consider them like supernova remnants and H2 regions that are actually the most contaminant sources for supernova remnant samples. And I combine them in 2 and 3 dimensions, where each dimension is an emission line ratio. And with machine learning, I found the line or the surface that best separates these two classes. Later on, we applied these diagnostics on news data of nearby galaxies, where we found some hundreds of supernova remnants. And using also theoretical models, we obtained an estimation of the shock velocities and electron densities. Currently, we are developing new diagnostics that take into account also planetary nebula, and we find that the most efficient classification can be done in 2 steps. So first, we separate shock from photonization models, as this surface here do, and then we separate slow from fast shocks and H2 regions from planetary nebula. Thank you.
Hi, good morning. So I'm going to present the work of my group of students at UNAMI and Ensenada. So it's going to be really quick. So if you have want more information, we have a QR code so you have the detail of those investigations. So the first one is Gustavo, who is working on comparative study of to compute ICF. This is what we have been talking about today with Jorge. Eric Del Caseron is working on identification of new planetary nebulae in the LAMOS survey. Then we have another, Gustavo is working on machine learning to detect the ICF. We have another work on machine learning by Diego Osvaldo Ochoa, who is looking for plus TGV stars using machine learning. We also have Vanessa, who is working on the analysis of dust in symbiotic stars, particularly the D-type stars. Amairani Leon is working on she finished the work on morphokinematic studies of planetary nebulae, and now she's jumping on something totally different, which is the observation of cataclysmic variable in TESS unobserved regions, TESS didn't map all the sky. And finally, the 2 last work are one from Marisa Cristal Botello, who is working on the characterizing the survival of exoplanets up to the white dwarf phase. And finally, we have Daniel Felipe Mera Valverde, who's working on the characterization, the detection of symbiotic stars in the galactic plane, and in particular the accretion type objects. So again, if you want more information, more detail on all those research, we have the QR codes here. Thank you.
Hi, I'm Federico Soto Vadillo from Ensenada, Baja California, Mexico. I'm a PhD student, and this work is about to study 12 planetary nebulae with bubble-like or suspected to be bubble-like morphology, in order to see if there is any correlation between the kinematics, morphology, physical parameters, and chemical abundances. To do that, we're using observation from San Pedro Martyr Observatory. With high dispersion, we obtain the morphology and the kinematics of the planetary nebulae. And for the low dispersion spectroscopy, we obtain the physical parameters and the chemical abundances. Here are 2 of the objects, Abell 43 and Low 8. We already have all the kinematics parameters of the 12 planetary nebulae, and we are working on obtaining the correct measurements of the spectra to obtain the physical parameters and the chemical. The next step is to do the 3D modeling of the sample of the planetary and more observations in some of the cases of the planetary nebulae.
Yeah, then are there any more announcements?
Yeah, just go for coffee break, and we resume at 10:50.
Yes. So, also, that the only from the station.
Yeah, in the back station.
No, I find it more important. So the worst very, so the one you told me, was this. Yeah, so I don't have, no, I have. No, I was more, so, I wanna, so I just, that I wanna, I say, okay, station. On the person.
Cuando vayas para el café, deja la presentación esa del blog.
Ok, sí.
Yes, yeah, you look, that's like feedback from the.
Ah, no, sí, sí, sí. Aquí es la segunda recomendación. Sí, sí, sí. Sí, sí, sí.
Which one? The one, the last one.
Different colors. Yes, exactly.
Yeah, okay, maybe that.
That's what I think also. I think he presented that is an online test. Yes, but then I thought maybe I can take the space both to this software because it's going to be good. I did the black one. So then I suppose I do not see the rebound. That's good. But that's the thing, but if I think it. Fast, I know it's not the original one.
Yeah.
So far.
Yeah.
And this one is the same one, and presented in that other complex, but I just changed the format, you know, giving most of the kind of a landscape. So I had to rearrange the. But it's the same concept. Yeah, so you are, told me that I was like, went back.
So hard.
I did. But I can't.
Like the spots in theory.
Do you remember how to do it?
Yes.
Well,
Thank you. That's what happened.
Oh, that's right, so each one, each one.
Yeah. The scaling factor.
Okay, so that's all better. My little. Yes.
So,
Right, so.
yeah, that, so. Search.
I was looking for. I was looking for the folder. But I think that. That's right. Yes. Yeah, 18. Oh, that's not very.
This is. Yes, that's the organization.
Yeah. Oh.
This one is not a good analysis. Yes.
That's what I searched for.
Good, like you're search for.